Welcome. In this video, we are going to understand concepts of stack, queue, and deque. Let's get started. First of all, we'll understand the concept, then we'll write a program, and then we are going to analyze how computer process our stack, queue, and deque. We'll understand the concept using a very nice website known as Visual Go, and we are going to understand stack first. On the website visualgo.net, in the linked list, we can understand stack, queue, and deque. Let's go to the website. Here we have to understand three important data structures which are based over linked list. The first is stack, queue, and deque. Let's switch to the stack first. So as the stack is represented, you can see that a stack is defined in a vertical format. We have got a random stack created, and if we point to peak, that means we can perform three functions with the stack. Either we can get peak of the stack, we can push value onto a stack, and we can pop values from the stack. Let me turn animations to slow mode so that you can understand the concept better. So once we need to identify the peak or top of the stack, we can execute peak command, wherein we'll get the head of the stack and tail of the stack, and peak will be identified as head of the stack. In case if you want to push an operation, let's say we like to push 53 on the current stack. So as soon as we execute, you can see that current head will be identified, new head will be identified, and new head will be made the current head. So here you can see that first of all a vertex will be created, head will be saved into temp.next, and the temp value will be stored into the head. So this is how we can insert one element on top of the stack. Stack is last in, first out. Once we try to perform a pop operation, so head will move from current head to the next head, and the temporary value will be removed. So this is how stack operates. Now in the animation you can see that the process has been done, and the process possesses O1, which is like excellent complexity. Now let's proceed further. We are going to write a simple program so that we can understand the following methods: how to create a stack, how to get top of the stack, how to push values onto a stack, and how to pop values from the stack. To do that, I'm going to use developer command prompt. Using this developer command prompt, I would like to go to my directory competitive, wherein I'm going to make a new directory, that is day 6. Within this directory, I'm going to perform my demos. So the first thing we like to create is, we like to create a program known as stack demo, and we'll call it as stackq.cpp. Within this stackq.cpp, we're going to write a program. So we'll include the header files, we'll include cstdio. We need to include stack in order to write the stack. We're going to use the namespace. Using namespace std, I'm going to write a main function, and this main function is going to return 0. Now in order to create a stack, we can simply call the stack type. We have to specify the type which will be stored inside the stack. So we'll be storing characters at the moment, and let me name the stack as S. Now we like to get started with a program, so we'll specify something like stack operations. Now what next we like to do, we like to push some values onto the stack. So using the push method, we are going to create a stack first. So let's say I'm going to push A, I'm going to push B, I'm going to push C on the stack, and finally I'm going to push D. So these 4 characters will be pushed onto the stack. Once the characters will be pushed, I would like to print top of the stack. So stack top, or we can also say stack peak is. In order to get the value of the peak in C, we can use the method or function s.top. S.top will point to peak of the stack, or you can also call head of the stack. So once we'll get the values, now after this operation we like to perform pop operations. So I would like to perform 2 pop operations, and then I would finally like to print the peak of the stack again. So we can do something like stack peak is %c/n s.top. So this is the basic operations which we can perform on a stack. We can push values onto a stack, we can pop values from a stack, and we can get top of the stack. So let's save the program. Let's go to the developer command prompt. Let's compile the program. And once the program is compiled, we can simply execute stack.q.exe program, and you can see that we'll get stack peak is D and B. Now we like to analyze this program first. In order to analyze the program, I'm going to use a debugger. So let's go to the debugger here. I'm going to use Ollie debugger. Let's run as administrator. I'm going to open the program, and I would like to execute my program from the competitive directory, that is day 6, and in the directory we like to open stackq.exe. So once the stackq.exe is running, you can see that I have one program stackq.exe running with the debugger. So as soon as we will execute instructions on our Ollie's debugger, output will be displayed on stackq.exe window. In order to proceed to analysis of our stack, we can simply right click on the dump. We can search for the referenced text strings, and we can see that we'll get the stack operation here. Let's double click on stack operations here, and what you can do is you can put a breakpoint at this instruction or at the offset so that we can understand what all operations are done. So here we can see that at this stage, at this instruction, A will be inserted onto the A byte will be inserted onto the stack. So I'm going to set a breakpoint here. Here 61 represents character A in ASCII. Then the next instruction is to move byte 62 into the base pointer into the address, and third 63 will be inserted, and finally 64 will be inserted. After this we are going to perform a stack top operation. So here at the push ECX we are going to get the value, and let's go to the next operation. Once the stack peak has been identified, now here some instructions will be executed through which our base pointers will be identified, so that the pop operations will be executed and base pointers will change, and ECX will hold other value for the top. And then finally what we are going to do, we are going to print the top of the stack. So this is how we are going to analyze our program. So let's just execute play so that we can understand. So at the moment the computer is at this instruction wherein he has printed out stack operation, and now we need to understand how things work. So once we reach here, you can see that this is the CPU instructions, this is the register section, third is the memory dump, and fourth is the computer stack. So at the moment base pointer is pointing to this and stack pointer is pointing to this address, and these are the values which will be executed. These could be values or addresses. Now we are going to step over the instruction. So let's say as soon as we struck over the stack operation will be printed onto the program here. So once we execute this call, the value will be printed. So as soon as we executed the call, you can see that stack operations is printed and it's pushed onto the stack. Once the values are pushed, now we like to see how A, B, C, D will be inserted onto the stack. So as soon as we proceed next, as soon as we execute this instruction, now we can see that value 61 will be inserted onto the stack, and the value 61 will be available just after your base pointer. So at the moment your base pointer is pointing to this, then on base pointer -1, that is one lower address than the base pointer, your value 61 will be stored. So here 61 is stored. Then as soon as we proceed next, so now value B will be inserted onto the stack. So you can see that here 61 and 62 are inserted onto the stack. So 61 is at EBP -1, 62 is at EBP -2. So we are moving from higher memory addresses to lower memory addresses. Now in the same way, if we proceed the next instruction, 63 will be executed and 64 will also be inserted onto the stack. So once the values are inserted onto the stack, you can see that at the moment, currently from the base pointer from EBP1 to EBP4, my A, B, C and D are inserted onto the stack. Once these values are inserted onto the stack, now we are going to perform some other operations, and that operation will be peek in order to get the top. So let's get the top of the stack. So we're going to get the top of the stack at this instruction. So let's just push the stack. So at the moment, now EAX data segment will, the value will be fetched from the data segment and will be stored onto the ECX. So you can see that the address has been stored onto the ECX once this instruction will get executed. So we are executing the instruction. So at the moment you can see that from the data segment, from the EAX register, a byte has been taken and it has been stored into ECX. This byte is known as 64 and this actually represents value number D. So at the moment you can see that the stack peak or the stack top is value number 64, which is D. So once we are going to execute the instruction and we are going to call the statement stack.q, so finally if we open the program here, you can see that stack peak is D will be identified. So the value stored was value number ASCII value 64, which denotes D. So once we have executed this instruction, at the same moment we can see that we have got all these 4 values 61, 62, 63 and 64 available on the stack. Now let's proceed with the next instruction. So if we go a little down, you can see that now after this instruction gets executed of top, now we are going to perform 2 pop instructions. So these pop instructions will be executed here, wherein you can see that the stack segment will change the EBP -1C value and will store the values into ECX. So ECX will be the counter register who will be pointing to the next, what you can say is the next head. So now what we can do is, let's just execute the instructions. So once we execute this instruction, the ECX points to a specific value, and that is, we can follow that in dump. And once we follow that in dump, here we have some values, and now this is the binary instruction which will be executed. So here is the value which will be executed, and now what next we have to do, so we are going to call this instruction. Once the call instruction has been done, now you can see that the ECX counter has been changed from 4 to 3. So this means now first value has been removed, and with respect to that counter 2EF, whatever the address here A3C is, let's just follow that in dump, or we can simply follow that in stack as well. So here we are pointing to this instruction, the counter is pointing to this point at the moment, and what we can see is the data register and the EX is pointing to counter number 3. So this means one value has been eliminated here, but actually from the program's memory D has not been removed. So we'll go to the next point. So you can see that pop operations just switches the counter value. So at the moment you can see that the EAX and EDX only remembers that only two values are available onto the stack, but practically all the values from A to D are available, but only registers maintain different values. So registers are maintaining the value 61 and 62 at the moment. So now once we have done the pop operation, now once we will execute this next instruction, that is our EDX, to identify the stack top, we'll get the stack top is the value number 2, and the value number 2 after EBP will be your 62. So let's just execute the next instruction. So as soon as we are going to push EDX here, you can see that EDX contains the value 62, which actually points to B, character B. So let's just execute the instruction, and once we executed the instruction, and as soon as the call is made, we'll get the value here on the console. So let's just execute the step over instruction, and now you can see that the stack peak is B is identified. So at this moment you can see that once push and pop operations are done, but actually from the real stack all the values remain same, but the registers maintain the value of individual values available at offsets. So this is how stacks actually work in computers, wherein pop does not physically remove the value from the program's memory, only the register EAX and EDX maintains the value of what has to be pointed. So I hope you understand the concept of stacks properly. Now let's just move to the next concept, which is queues. So stacks are the data structures which are based on linked list, but they are vertical in order. We have one horizontal data structure as well, and this is known as queue. The beauty of the queue is it has a head and a tail. You can add elements at the tail and you can remove the elements from the head. This is like first in, first out. So now let's just identify peak. So as far as queue is concerned, we have the following 4 operations available. We can create a queue, we can get head of the queue using peak, and we can get the value in C++ using queue.front, and we can get the value in C++ for the tail as well, and we can execute the method or function queue.back in order to get the tail value. Now once we get the peak value, we can enqueue and we can dequeue the values. In order to enqueue, we can add the value at the tail, and once we dequeue, we remove the head and moves our current head to the next value. So let's just perform the operations. So once we have executed peak, head will point to the peak. Once we enqueue, let's say we want to add 57 to this queue. So once we add 57, a temporary value will be added and current tail will be changed to the next temporary value. So now what next we have to do, this is like the enqueue process. Once we dequeue, so the current head will be converted into a temporary. The temporary dot next will be taken as head and the temporary will be deleted. So this is the operations which can be performed on queue. So now what next we want to do, we like to modify the program and we like to proceed next. After this pop operation, now we like to execute some more tasks, which is queue operations. In order to perform the queue operations, we like to have the header file, that is queue, and we want to initialize a queue here. To initialize a character queue, we can specify it with this format and we can give it a variable name known as queue. So first of all, we are going to push some information on the queue. So we can push the values into queue using push function. Then we are going to push another value, let's say B. So I'm pushing value onto a queue at the moment, and let's just say D. So we have pushed 4 values onto the queue, and now I would like to show you the peak or the head of the queue, so we can get the head and tail both. So let's just point to that. Head of queue is %c/n, and let's just point it to q.front. Using q.front, you can get head of the queue, and in printf you can get tail of queue is %c/n, and you can get that using q.back. Now once you have got the queue information, now what you can do is you can simply do q.pop in order to remove the values. We can remove the values from the method pop, and then finally we like to print the values again. So using pop you can remove the values. Now we like to print the value of the head again. Head of queue is %c/n, and I would like to get the front so that you can understand the change in the values, and I would like to print the tail again. So let's say tail of queue is %c/n, and that will be q.back. So q.back value will be same, but the front will change because we have removed 2 elements from the queue. So now we have written a program. Let me just close the program from here so that we can recompile it. We're going to save the program using Control S. Let's compile the program. Once the program is compiled, now I'll go to Ollie's debugger. Before Ollie's debugger, let's just run the program. So once we do that, so first of all we'll get that head of the queue will be A and tail of the queue will be D. But after 2 pop operations, A and B will be removed from the queue, and queue will be pointing the head to C, and tail of the queue will be pointing again to D. Now let's understand this data structure in Ollie's debugger. So we are going to run the program again. Let's run the program. We are going to search for reference text strings. We are going to go to queue operations, and we are going to set up bookmark here. Let's set a breakpoint here. So here I'm going to change the address value to BBP. This is what the base pointer is. This is your current stack pointer is. Some memory has been allotted to your program. So here onto the memory you can see that from EBP -1 to EBP -4 you have got your stack created, and now just after the stack we are going to create a queue. So let's just increment. So we have this instruction 61, 62, 63, 64. So we have like 4 programs will be done. So let's just run the program. So now I'm going to execute 61 here, so that 61 will be inserted at EBP -5, 6, 7, 8. So EBP will point to EBP -5. So now let's just insert this value. So once I have inserted 61, you can see that at EBP -5 I have got A inserted. Then I'm going to execute next instruction wherein I've got B inserted. Then I'm going to run the program, and I'm going to perform C inserted 61, 62, 63, and then finally I'm going to run the program, and I'm going to perform D inserted. So now once these values are inserted, you can see that pushing values onto a stack and pushing values onto a queue is exactly similar. In understanding the stack in Q, stack is a vertical structure and Q is a horizontal structure, but as far as computer memory understands it or arranges it, the arrangement is like quite similar. The only changes will be the values which will be kept in registers after assembly is performed. Now, once we have inserted these values from 61 to 64 ASCII, that is from A to D, now we are going to perform some pop operations here. So in the pop operation, the base pointer will change, the stack pointer will change, and your values into the ECX will change. So let's just put the break points here. So now once we are here, so value of EBP minus 20 from the stack segment will be hosted onto ECX. That means EBP minus 20 contains some instruction, and that instruction will be hosted onto the ECX. So let's just call that instruction. So once the instruction is called at 011B2290, so some instruction will get executed, and the value of the EAX, that is the ECX, which we can follow in dump, that's the program here, will be executed, and from here we have a memory address or something which we can modify or search for. Now, so here once the pop operation has been performed, you can see that just like queues, the values are not removed from here. We are going to perform one more pop operation again, and now after performing the pop operation, we are going to compute head of the queue using the data segment EAX register, and we are going to store that into ECX. So once we have executed this instruction, you can see that on the ECX we have got the value 61. So 61 actually points to A character. So the back or head of the queue is actually pointing to the value 61, that is A. The value has been pushed onto the stack. So let's just press enter and let's just call head of the queue. And once we have called the head of the queue, you can see that head of the queue is A at the moment. Since we have inserted A, B, C, D onto the stack, and once we have identified head of the stack, so A has been identified. Now we are going to perform the next operation in order to identify tail. So here you can see that the tail will be identified using the counter register, and then value from the data segment EAX will be loaded onto EDX. So let's just execute the instruction. We are holding the value into ECX. So ECX is pointing to some value, some instruction, and after the instruction gets executed, we're going to get the value, get the byte from this pointer data segment, and we are going to push that onto EDX, and then we'll push EDX onto the stack. So let's just push EDX, and at the moment EDX is pointing to value number 64. So data register keeps track of the tail, and the tail is the value 64 that is pointing to D. So now you can see that you have got head and tail, and you can see that the value will be printed as soon as we execute the next instruction. So as soon as we executed the call, we have got the tail of the queue is D. Now we are going to perform the pop operations by changing the base pointers from the stack segments into the ECX registers. So LEA stands for load effective address of stack segment EBP minus 20 into ECX, and so that we can perform the counter operations. So once the instruction has been executed into ECX, some value has been stored, and this value is something 82C, that we'll understand here. So 82C is pointing to some address, and that is something like 8A78D. that will be some instruction which will be executed. So now once the pop operations is performed, so 2 times the pop operations are performed and the counter register has been changed, and after they have been performed, now we are going to execute the value of the byte in the EX into EAX, and that will be pointing to your 63. So at the moment the head will be pointing to the value number C. That means when you have performed pop operations, A is removed and B is removed, and C is acting as head, which has been returned through the EAX register. But you can see that just like stack, the values which were stored into the queue are also available on the memory, but the register EAX is currently pointing to the header, and the header value is C, that is 63. So now let's just execute next. So once we have executed the calls, you can see that the values has been identified, and in the same way tail will be identified. So in the tail, ECX value will be registered, so tail is 64. So here you can see that EAX was containing the first input and ECX was containing the second input. So it contained the head and ECX contained the tail, and you have got both the values posted onto the stack. So this is how you can identify the values, but again I'm pointing to this thing that from EBP minus 5 to EBP minus 8 the values are still available on the memory, on the stack. So now I hope you understand the point. So you have got the tail information here, and you can see that once we have created a queue, the queue head was pointing to A and queue tail was pointing to D. We have performed two operations, so that is first in first out operations. So the first two elements have been removed, and the next head of the queue is pointing to C, and tail of the queue is pointing to D. So if we compare stacks and queues now, so stack is a last in first out and a queue is a first in first out. In both the cases, values will remain in the memory in the offsets wherein they have been pushed, but the register values will change with respect to the binary code executed. Now in the same way we have one more data structure that is known as Deque, and the beauty of the Deque is it is a doubly linked list. So doubly linked list has one benefit: you can identify head and the tail. Deque gives you an opportunity to add or enqueue the element in the front and the back as well, and you can dequeue the elements from the front and back as well. So we have got a deque created, so we can point to the peak. So using the front you can get head of the deque, and you can point to peak and you can identify back, that means tail of the deque as well. In the next option you can enqueue an element, so you can enqueue the element at front as well. So you can push front, and in a deque you can push an element from the back as well. So in this way element can be pushed from the front and it can be pushed from the back as well. So now if we perform a deque, we can remove an element from the front as well, and we can remove an element from the back as well. So this is deque for you. So deque is a doubly linked list wherein you can get head of the deque, you can get tail of the deque, you can insert an element at the head of a deque, you can insert an element from the tail of the deque, you can deque an element from the head, and you can deque an element from the tail as well. So deque is a very important data structure used for competitive programming, and let me just guide you how you can simply write a program in order to understand deque. So you can use the package name q in order to create deques as well. To create a deque you have to use the name deque, you have to provide the character, and let's call d as our deque. So at the bottom of the program we are going to execute a statement, let's say deque operations /n. Now once we are performing the deque operations here, let's just get started with the deque operations. So what we like to do here in the DQ operations, first of all, I would like to push the values in the front. Let's say I pushed a value A in the front, then I push a value B in the front, then let's say I push a value at the back, so let's call it as C, then I pushed the value again at the front, D. So we will be inserting the values onto the stack, onto the memory stack, and then we are going to analyze how we can push the value onto the front and the back of a DQ. So once the value has been pushed, now we like to print some statements. Let's say front head of a DQ is %c/n, and now I would like to do something like, let's say we're going to print the value, so we can simply get the front value of the DQ, and in the same way I would like to get back of the DQ. Back tail of DQ is %c/n, and I would like to get the back as well. So once we have got the head and tail, now we would like to remove the values or pop the values from front and back. So let's say I would like to pop the value from the front first. Let's say if I pop the value from the front, A will be removed, and then if I pop the value from the back, then D will be removed, and then I would like to print the front head and the back head, so we'll get B and C as the front and the back. Because A will be removed, we'll understand which has been removed, because we have added A, then we have added B at the front, so it becomes BA, then we have added C, so it becomes BAC, then we have added D, so it's like DABC. And now once we have removed the front, so D has been removed, C has been removed, AB will be left out. So we'll just check that, just save it, compile the program, cl stackq.cpp. Before compilation, I would like to remove the program from Ollie's debugger. Let's just go to the program here. We're going to print the stackq.exe. So we'll get front head was, earlier it was D and C. So let me just get set with the program. So we have put that onto the front, so D would be the front, and we have put the value onto the back, so C was the back. So D was the front and C was the back, that's clear. And now once we have inserted front head of a DQ is B, so once we have popped in, so the front was D has been removed and A has been removed. The front has been removed, then we have the C. So once the front has been removed, we'll get front as A and the back as C. Since we have performed two pop operations, so we have popped from the front first, so the front was D, D would have been removed, and then we have performed pop from the back, so we did C. So then we'll get the head, the front, so front would be B because it has been added after A, and back will be A, so we'll get B and A. So let's just understand the point. So here we did that. So I hope you are clear with the concepts of DQs. And now what next we like to do, we have compiled the program. Let's just run the program. We'll just run the program again. We'll search for the reference text strings. We'll go to the DQ operation. We're going to set a breakpoint here. So at the moment I would like to show you how this is your stack, this is your queue, and now once I have executed this I would like to push the EDX at the moment here, so I would like to run, and at this point I would like to show you that this is your stack, this is your Q, and this is your DQ. So all the values are arranged in the similar manner. The only cases is with the register. So now what we'll do, we are going to get the pop operation. So I would like to get the value which will be at head of the DQ. So at the moment head of the DQ will be, let's just run. So head of the DQ will be contained in the EAX. So EAX is actually containing 64th value, which is this. So it does not depend on how you inserted the values, it depends on the pointer who's containing the value. So DQ, what exactly it is doing, the final code you have executed was front. In the front you would have got D, so here D has been returned in the EAX. And now what next we'll do, we need to get the tail. So for tail, let's just play the program. So for the tail in the ECX, you can see that we've got 63, and this is because C was inserted at the back. So we've got that C as the tail. And now what next we'll do, after doing this, we'll do the pop operations. We'll pop from the front and we'll pop from the back. So once we'll pop from the front, D will be removed, and once we'll pop from the back, so at the back C is there, so we are going to remove C. So D and C will be removed and we'll get B and A. So B will be front and A will be back. So let's just do that. So here we'll go to this point here, let's just double set a bookmark here. So at this value you can see that EDX contains 62 and 62 is B, and here your B will be returned. Let's just execute this instruction. So once a call has been performed, you can see that B will be printed out, and now as the base pointer suggests, you can see that the values are same for stack, Q and DQ, only the address registers, the accumulator, counter and data registers are holding the values of your top and head, tail values of the data structures. So now once we go at the back here, if we go to push EAX or something, so here at the statement at call I would like to execute this instruction, and at this moment you can see that it has been pointing, it has executed the tail, and the tail would be your element number. The head has been done. Now let's execute that instruction. So once the call has been made, you'll get A. So this is how your DQ is arranged. You can insert value at front of a DQ, you can insert value at the back of a DQ, you can remove values from front and back, and you can get the peak, that means the head value and the tail value as well. So this is how instructions are performed on stacks, Qs and DQs. So I hope you understand the data structures properly. Now you know how stack, Q and DQ works. You can understand it animation wise as well. You have written a program as well, so you know how you can push values actually through a program, and you have analyzed that how computer processes it, how registers deal with the values, and how memory stack holds the value which has been inserted onto the memory stack. So thank you for watching the video. For queries, write us back.